Throughout our study of complex analysis, we focused on one way of visualizing complex functions, namely as a mapping of points in one complex plane to points in another. We used two planes, the pre-image and the image, to describe this mapping. Our goal is to introduce a completely new way of visualizing complex functions, specifically focusing on how they can be used to visualize complex integration. We hope to produce new insight into how to think about complex functions, and we'll end up finding that there are actually many surprising connections with physics. Let's try and visualize a complex function f of z in a single complex plane. The input value z will be a point in our complex plane, but instead the value of z will be pictured as a vector emanating from z. We now have a vector field of f. So let's take a look at the example e to the z, or the complex exponential. Let's take a point z, in this case equals 1, and then draw a vector of f of z coming from that point. Let's do this with a few more examples. As you can see, we can start to see a vector field. Let's try it with just a subset of the points in z. As you can see, the vectors with very long magnitudes get kind of cluttered, and it gets hard to see what's going on. So something that we do is we actually artificially shorten the vectors with long magnitudes so that it looks kind of something like this. Keep in mind that this is not going to be the final representation, so let's call this the original vector field representation for now. We're also going to be adding more touches to this visual, so just keep that in mind. The original vector field representation remedies a shortcoming in the pre-image and image complex mapping. We are able to get a better feel of the overall behavior of a complex function as we inspect its vector field. However, there's one small caveat, and that is where Polya vector fields actually come into play. But before that, let's actually have a quick aside on fluxant work. Suppose we have a complex function f of z with a vector field f along a curve c in the complex plane. The work of f along c is the total magnitude of the field tangent to the curve, or given by this integral, where t is the unit tangent vector in the direction of the curve, and ds is the instantaneous differential length of the curve. The flux is just the same thing, except for it's the magnitude of the field normal to the curve, and n in this case is a unit normal vector in the direction of our path. So as you may have guessed by now, the caveat does lie in complex integration here. So consider the integral f of z over this curve c. So we can parameterize f of z given by this equation, where the angle beta is the angle the vector field f makes with the positive real axis of z, and dz is parameterized by the following, where alpha is the angle that dz makes with the positive real axis, and ds is the differential length along c. And thus we can express our integral as that equation. We will show a drawing in just a few moments that will help explain this much better. Integrating this term involves the addition of angles, which isn't really easy to visualize. It is, however, easier to visualize the difference between two angles, in this case theta equals alpha minus beta, as this angle is used to calculate helpful quantities, in this case the work and the flux of the curve, using the cosine and sine of this angle. This will make a lot more sense in just a moment when we show this visual, but here, let's introduce the Polya vector field. So this is our big reveal. To better explain this angle theta, instead of drawing f of z at z, what if we draw f bar of z, or the conjugate of f of z? So more formally, for function f of z in its real and imaginary parts, let's define the Polya vector field as follows. Just by simply plotting the complex conjugate of f of z, we get much more information that will help us visualize complex integration. So as promised, here's the graphic to better explain the intuition behind the angles alpha and beta and how we get theta. Keep in mind that we are using h as our complex function here. Take a careful look at how we get angle theta from the addition of alpha and beta, and how we get the angle negative beta from the complex conjugate, and how it's the angle from the real axis. Also notice how the angle theta lets us obtain the work and the flux given by h dot t and h dot n of the complex curve. So with that, let's re-express our integrand. So first defined f bar as the following, the magnitude of f bar times e to that negative angle beta that we've defined before. Then we can define f bar dz as the following, and that simplifies to the magnitude of f bar times e to the I theta, which is the angle theta that we've saw in the graphic, the angle between dz and f. So take a look at these equations and make sure they make sense to you. So next, let's redefine our integral. So given that f dz equals the following, then let's rewrite the integral of f dz on the contour of c as the following set of equations. Notice how we actually get something pretty interesting here. Notice how the real and imaginary parts of each of the term in the integral are the work and the flux of the Polya vector field for the corresponding element of the contour. So our integral now can be expressed as the integral of f dz is the work of the Polya vector field along the contour z plus I times the flux of the Polya vector field along the contour of z. Cool, isn't it? So given this definition, we can examine a certain contour along a Polya vector field and then quickly get a feel for the value of the integral just by looking at how much field flows along and across the contour. So let's take a look at the Polya vector field of our old friend, the complex exponential. See how we've color-coded the vectors such that red vectors are a large vector magnitude and green vectors are a shorter vector magnitude, and yellow and orange are somewhere in between. Just take a second to appreciate how cool that looks. So now we can start approximating the value of an integral along some contour. So let's start by drawing a contour. In this case, a semicircle. Now let's take a look if we can see how much vectors flow into this contour. In this case, we can see that there's a lot of flux into this contour, which means that the imaginary part of this integral must be large. So let's consider a simpler function this time, f of z equals z, or just a complex mapping to itself. Here's a Polya vector field of f of z equals z. So let's see if we can approximate integral along some contour, in this case, a whole circle. See if you can visualize the work and the flux along this contour and take a guess on what you think the value of this integral is. How about for f of z equals z squared? Next, let's take a look at the Polya vector field of f of z equals sine z. Once again, let's draw a contour and let's examine the flow through this contour. Pretty cool, huh?
So we now have a visual intuition for complex integration, but let's pose a different question. Given a Polya vector field of a function f, how can we tell whether or not f is analytic? Before we answer this question, we need to talk about two geometrical quantities of a vector field. The divergence of a vector field is a measure of how much of it flows in or out of a surface. This quantity is also known as the flux density of a vector field. In contrast, the curl of a vector field is a measure of the tendency of the vector field to rotate. This quantity is also known as the work density of the vector field. Notice how the two rings on the outside rotate counterclockwise, while the two on the inside curve clockwise, leading to positive and negative curls respectively. Now we'll introduce a relation between Polya vector fields and analytic functions. Let f be a complex function, then f is analytic if and only if its Polya vector field is both divergenceless and curlless. In other words, this field has no source and is irrotational. The divergence and curl of the Polya vector field of f are as follows. When these two quantities vanish, the relationships become the Cauchy-Riemann equations exactly. Thus, the Polya vector fields of f have zero divergence and curl. F must be holomorphic and therefore analytic. Here's a visual interpretation of Cauchy's theorem. If f is analytic everywhere inside a closed contour K bounding a region R, then its flux and work densities in R are both zero. Therefore, based on the equations we've derived, the integral around K must vanish. Physically, this means that the net amount of fluid that flows through K is zero, and that a projectile fired around K from a point P returns the same kinetic energy it left with.
So far, all of the functions that we've shown here were actually holomorphic. So let's take a look at e to the z one more time and let's draw a closed curve. Notice that all of the flux coming into the contour leaves at some point, meaning that the net flux is zero. You can also tell that the work is also zero and that any closed curve drawn at any point in this vector field results in a net flux of zero and work of zero. For z, the same holds as well. And also for z squared. Let's now consider a function that is clearly not analytic, in this case z bar. Notice off the bat that this vector field clearly has a divergence of a positive value, meaning that this vector field acts like a source coming from the origin. Therefore, the net flux around this closed curve is non-zero, and therefore this function is not holomorphic.
Let's transition to showing some applications of Polya vector fields. First, let's show how we can think about the area bounded by a curve C in terms of the flux through said curve. Recall the following result from our previous homework. The integral of z bar about a curve C is equal to 2ia, where a is the area enclosed by the curve C. We'd like to show this result using Polya vector fields instead of Green's and Stokes' theorems. We've previously mentioned what the work and flux densities are, but let's formally express this integral in terms of these quantities. The integral of z bar along a contour C is equal to the work the vector field of z does along C plus I times the flux of this field through C. These terms can also be expressed as the integrals of the work and flux densities respectively over the region R enclosed by C. The divergence and therefore flux density of this field is 2, while the curl and therefore work density is 0. Thus, the flux of this contour is 2 times the area A bounded by the contour, and the total value of this integral is 2I times this area.
Now, let's examine a concrete example of this new way of looking at this result. First, let's start with the polyvector field of z bar with much more denser vectors, and let's start by adjusting the colors of the vectors so that the gradient of the changes of the magnitudes are a little bit more clear. Then let's draw a contour. The shape of this contour is chosen so that the values of the work in flux are obvious. Next, let's mark our values. The shorter radius of the arc is B, and the longer radius is A. The angles of this arc is going to be the value phi. As you can see, the work along these straight line segments are equal and opposite, and there's no flux along these line segments. Conversely, along the arcs, there is no work across these arcs. However, there is a positive flux. And this is because the speed of the vectors coming into the shorter arc is less than the speed of the vectors coming out of the arc. And therefore, we have a net positive flux. Let's show this a little bit more formally. The larger arc has a length of a times phi, and the speed of the fluid or the vectors crossing it is also a. Therefore, the flux across this arc is a squared times phi. We get these values from the values of the vector field. Similarly, the flux across the smaller arc is b squared times phi. So the flux, which also can be thought of as the fluid out minus fluid in, is equal to this quantity, which is also equal to 2 times the area of this enclosed region.
Next, let's show how Polya vector fields apply to winding numbers. Recall from class that the integral of 1 over z dz about a curve L is equal to 2 pi I times the winding number of this curve L about the origin. From previous work, we've shown that this integral can also be expressed as the work the vector field of 1 over z bar does on this curve L plus I times the flux of 1 over z bar through L.
Let's take a look at the Polya vector field of the function 1 over z. Notice how the vector field is similar to that of z bar, except the vectors get smaller as they move away from the origin. We'll go over this in a second, but the divergence of the vector field is undefined at the origin and 0 everywhere else. Without going into too much technical detail, this Polya vector field of 1 over z is a source of strength of 2 pi from the origin.
The first thing to note is that the source of this field is pure flux, which means that it is a net work of 0 in every closed contour, regardless of whether or not it encloses the origin. With this in mind, given some closed loop, if the loop does not enclose the source of the origin, just as much fluid flows into the contour as out of it, as its divergence is 0, so the net flux for this loop is also 0. If this loop does enclose the origin, it intercepts the full 2 pi of fluid pumped in from the origin, which means that the loop accrues 2 pi of flux for each time it encircles the source. This gives us exactly the result we were looking for. Because our integral is equal to I times the flux of this loop due to there being no net work done, we get that this value is 2 pi I times the winding number of the loop. Finally, something interesting of note. We know that 1 over z is holomorphic everywhere on the complex plane except at the origin. Because of this, the divergence is not defined at the origin. Although it seems like more fluid is flowing into the sphere than out, the magnitude of the flow is also shrinking as it radiates outwards, so the total fluid in and out of the sphere is the same. This is not the case when we include the origin. Therefore, it makes sense that a loop enclosing the origin produces a non-zero flux and thus leads to a non-zero integral, while a loop that does not enclose the origin produces zero flux and leads to an integral of 0. This idea can be applied to any curve that winds around the origin any number of times.
Before we end off, let's just recap on what we've learned in this video. We've established a visual basis to visualize complex functions through their Polya vector fields. We've shown how Polya vector fields help us visualize complex integration. We described the sourcelessness and irrotational property of Polya vector fields of analytic functions. We've shown a new way of thinking about Cauchy's theorem in terms of Polya vector fields. And we've applied Polya vector fields to think about area as flux and winding numbers as flux. All right, thanks for watching. We hope you enjoyed and we hope you learned something new.